Hi there. Welcome to the Elimination Reaction simulation. Here you will learn how to predict the reaction products in common elimination reactions in organic chemistry. When completed, you should also be able to explain the reaction mechanisms of so-called E1 and E2 reactions, and apply Zaitsev's rule, which is central to elimination reactions. Sounds fun, right? This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will pop up whenever there are instructions to read. You can select whatever type of audio you prefer. To mute an audio option, just deselect it. Click Continue to start your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a Labster simulation? Perfect. Then let's get started with your first mission. I've just received a message from my research friend, Kim. They have an issue in their lab that we hope you might be able to help out with. Let's go see what she's up to. Go talk to Kim by the table.
Hi there, good to meet you. I'm a research engineer here at the Polymer Research Lab. We study polymers, which are large molecules that are built of repeating subunits. We use them in the production of cheap and durable building materials and sanitary installations, like water pipes. We're working on making these materials available in locations where extreme weather events are a threat to the water supply. But if we want to succeed, we really need to cut the production costs. In one of the processes, we're using cyclohexene, which we make from cyclohexanol with phosphoric acid through an elimination reaction. We want to see if we can find something other than phosphoric acid because phosphor, as a limited resource, is becoming prohibitively expensive. We have been trying with hydrochloric acid, but get weird side products, like this one. Could you help us find out how elimination reactions work, why we are seeing weird byproducts when using hydrochloric acid, and what a useful alternative could possibly be?
Interesting. I hope you're up for this challenge. Let's go back to the main lab room and see what we can do for Kim. When you're ready to return to the main lab room, click the small plant on the table. So that you can help Kim, we need to bring you up to speed on the fundamentals of elimination reactions. Let's start by brushing up on a few key concepts of organic chemistry over at the functional groups poster. Go to the functional groups poster. Explore the functional groups poster. Raise your lab pad when you are done. Are you ready for some questions about organic chemistry? Great. Let's see what you've got on concepts within organic chemistry reactions. What's the main functional group in cyclohexene? You can find the structure of cyclohexene in the Media tab, in the image showing the elimination reaction with phosphoric acid. That's right. Cyclohexene has a carbon double bond, which makes it an alkene. Cyclohexanol belongs to the alcohols. In chemical reactions, what is a leaving group in the molecule of interest? Brilliant. In elimination reactions, it's very important to keep an eye out for these. Do you know what a carbocation is? You've got this. Alright, let's get you ready to work in the lab. You can always return to this poster later on if you're more curious about the functional groups. Locate the lockers and open one of them. Raise your lab pad for more and find a lab coat inside the lockers and pick it up. Pick up a pair of safety goggles. Alright, on workbench 1, I've set up a basic distillation unit, similar to the one in Kim's lab. Go check it out. Enter the main lab room. Go to workbench 1. Before interacting with the lab equipment, you should put on some gloves. Find a glove box and click the distillation setup. In this distillation setup, we've mixed cyclohexanol with a few drops of phosphoric acid. Wondering how it works? Check out the different parts of the distillation setup. Raise your lab pad when you're ready to continue. Have you checked out the different parts? Great. Then let's see if you can answer a few questions about the setup. Where does the elimination reaction occur? Exactly. This is the reaction vessel where we've added cyclohexanol and phosphoric acid. Where do you think the cyclohexene product will be located when the reaction is finished? You've got this. The cyclohexene ends up in the round bottom bottle on the right, as it has a lower boiling point than the other compounds in the reaction mixture. Let me show you a more general version of the elimination reaction. Often, there will be a base that extracts one of the side groups, which we also call substituents. You can always revisit this image, and other key images you see during the simulation, in the Media tab here on the lab pad. Which sentence would you say best describes a typical elimination reaction within organic chemistry? Exactly. Well done. Two substituents are lost, one on each of two neighboring carbon atoms, and a double bond is formed between the two carbon atoms. Alright, now it's time for you to really dig into a real elimination reaction. I have prepared a little challenge for you at the hollow table. Go to the hollow table. Your first mission today will be to carry out an E1 elimination reaction. Worry not, I will assist you. The acid-catalyzed dehydration of cyclohexanol to cyclohexene that Kim is working on is a type of E1 elimination. Acid-catalyzed dehydration simply means the net loss of water from cyclohexanol to give us cyclohexene. We will work with the alkyl halide you see here as an example though, and you can follow the reaction in 2D on the whiteboard behind the hollow table as we make progress. First, you will have to identify the leaving group of the molecule. Could you do that? Pick up the leaving group marker, and place it on the part of the molecule that could work well. Nice, good job. Alkyl halides are commonly used in elimination reactions, because halides can be really good leaving groups. Quick question. What happens to the electrons in the bond between the leaving group and carbon, when the leaving group leaves? That's right. The electrons go with the leaving group, which in many cases means that it will carry a negative charge. Try and think of an example where this will not be the case. Now click the bond between the leaving group and the rest of the molecule to break it. Very cool. Since we moved some electrons, let's consider whether or not we need to add some charges to the molecules. Add the correct charges to the two relevant atoms, and click Done when you think you've got it. Exactly. You have now successfully eliminated bromide from the molecule and added the correct charges. This was the first step in the elimination reaction. As you can see, the main molecule is now a carbocation. The next step involves a base, which will extract a hydrogen atom. Let's get it on the hollow table and get rid of bromide. It's no longer of interest to us. Click on the base. Great. The carbocation we've created is not stable, and it really wants to react with a nucleophile, such as this base you just clicked. Let's make it happen. Click the electron pair on the base to activate it. Now choose the correct part of the molecule the base will react with. Brilliant. Did you get that? Hydrogen was extracted by the base, thus eliminating it from the molecule. What happened to the electrons that formed the carbon-hydrogen bond though? Yeah, you got it. The electrons move to form the carbon-carbon double bond. The type of elimination we just went through was an E1 reaction. There's another main type called E2, which works a bit differently. We'll get to that. Did you wonder why the double bond formed where it did? Couldn't it just as well have formed somewhere else in the molecule? We will explore this a little later, but first I will test your reasoning ability. Go to Workbench 2. Here you see 5 containers with different alkyl halides. You can check out the contents of each container by hovering over it. Try it out. Check out the containers. Raise your lab pad when you're ready to continue. Are you ready to continue? All right. All of these 5 alkyl halides can undergo elimination reactions. Some of them are far better starting materials than others. Which ones, though? Place the container with the least E1 reactive molecule on the right. Nicely done. Can you do it for the other 4 containers as well? Place the 5 containers so they are ordered by increasing E1 reactivity, with the highest reactivity placed on the left. Good work. So, what was determining the order of reactivity towards the E1 reaction pathway? Exactly. The trick with the E1 reaction, similar to the SN1 reaction which you might know, is that the intermediate carbocation has to be as stable as possible, as it's the formation of this ion that's the rate-limiting step in the reaction. To spice things up a bit, I also included chlorine as the leaving group for one of the compounds. As you correctly determined, a better leaving group increases the reactivity. Since you're so good at this, I wonder if you can figure out how it works for E2 as well. What I can tell you about this reaction is that it does not go through a carbocation intermediate, but happens only in a single step. What do you think the order of reactivity would be for the 5 compounds for the E2 elimination reaction? Genius. When only looking at the substrate and leaving group, reactivity towards the E2 reaction is actually the exact same as for E1. Because you're doing so great, I've created this cool rock star for you. Keep it up. Be aware that in little challenge you just did, we were only focusing on the substrate and its leaving group. There are other important factors affecting the main reaction pathway, in particular the solvent and base used. The effects are very similar to those of nucleophilic substitution reactions, and we will not cover them here. In order to evaluate whether an E1 or E2 reaction will actually occur, or if, for example, a substitution would be the main pathway, we would need to know the full picture. Alright, let's move on to your next mission to understand eliminations. Go to the wall screen in the center of the lab room. In elimination reactions, there is something called Zaitsev's rule that determines where the double bond will form. See if you can figure it out here at the screen. I will take you through 4 rounds, where you have to select the correct reaction product. Click on the main elimination product of the reaction. Good choice. Let's see if you can handle the next one as well. Click on the main elimination product of the reaction. Right on. Again. Click on the main elimination product of the reaction. That was a more tricky one, but you chose wisely. Click on the main elimination product of the reaction. Brilliant. Looks like you've got this. So exactly what pattern did you observe for the main elimination products? You can go back to the different rounds on the screen to check the result again. That's right, and that's what's called Zaitsev's rule. The reason is, put simply, that the more substituted product will be more stable. The underlying reasons for this are a bit more complicated and beyond what we will go into here. Great work. It seems that you have a pretty good grasp of the basics of elimination reactions. I'd like to show you the E2 reaction type now, how it differs from the E1, and why that's important. Go to the hollow table. Do you remember how the E2 reaction was different from E1 on a general level? Indeed, it does. This can be a bit confusing, but it's because the number does not refer to how many steps there are, but how many reactants the rate limiting step depends on. And for E2, that's both of the reactants. Zaitsev's rule also applies to E2 reactions, and the type of substrates are the same for both types of reaction. To get working with the E2 mechanism, let's get the molecule back to where we started. Click back on the hollow table to rewind the molecule to its original state. Excellent. As you know, this molecule could technically follow an E2 pathway as well as E1. But we can change it to make E2 more favorable. How would you change it to make it more likely to follow the E2 path? Right on. This will make formation of a carbocation less stable, and therefore discourage the E1 path. There are other ways to manipulate a reaction to mainly follow E1 versus E2. Check out the theory if you want to learn a bit more about that. Let's make the change to the alkyl halide. Click the part of the molecule we should change. Right on. We could also have changed one of the other side groups. The main point here is to lower the stability of the central carbon in a carbocation intermediate where the leaving group has left. Having fewer carbon side groups helps with that. Let me fix the molecule for you. Alright, I will now enable the E2 elimination reaction on the molecule. Remember that the mechanism is also shown in 2D on the whiteboard for comparison. Check out the E2 mechanism by clicking the play button. Cool, right. I will now ask you a few questions about this mechanism. You can play it back and forth at your will, and examine the details. Why is the double bond being formed between the 2 carbons in the middle of the carbon chain? That's right. In a real reaction, we'd usually see a mixture of different products forming, but the one that followed Zaitsev's rule would be the major one. What is the configuration of the product around the double bond? Exactly. In an E2 reaction, a product with trans configuration will be far more dominant, due to the fact that the leaving group and the base removed hydrogen will tend to be anti-paraplanar. This is a special trait of E2 compared to E1. The E1 reaction doesn't have this selectivity because the formed carbocation intermediate could proceed to either the cis or the trans isomer. Alright, really well done. As you've hopefully noticed, the products of E2 reactions are very similar to those of E1. However, the dominant reaction pathway can highly impact the exact configuration of the main product, and the relative number of different products formed. I think you're ready to get a crack at Kim's problem now. As you might recall, they were trying out alternative acids, specifically hydrochloric acid, in their elimination reaction that converts cyclohexanol to cyclohexene. Why do you think they're seeing this reaction product when using hydrochloric acid with cyclohexanol? That's it. The chloride in hydrochloric acid can act as a nucleophile and substitute the hydroxide group in what's called a nucleophilic substitution reaction. This was not happening when using phosphoric acid. To find a likely alternative for Kim, we need to come up with an acid where the corresponding base will not act as a nucleophile. Which of these acids might be the best as an alternative to phosphoric acid? Exactly. The corresponding base species formed with sulfuric acid are too bulky to work well as nucleophiles. This will mean the elimination reaction is favored instead. Alright, let's head back to Kim and tell her about your findings. Click on the molecule and I'll take you back to Kim.
Genius. Of course, the side products are due to competition from a substitution reaction when using hydrochloric acid. Using sulfuric acid makes a lot of sense. We'll need to run a lot of tests before we can put it into production, but it sounds very promising. Thank you.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.